This is Chapter 1, Section 1.3, Combinations, the Binomial Theorem. So previously we talked about permutations, and permutations is essentially a combination where order makes a difference. So for instance, if I'm dealing with a pool of 10 candidates and the order in which I choose them makes a difference because I have a president, vice president, and secretary, then I have to use the permutation formula that says 10 factorial over 10 minus 3 factorial. And remember, when we did this previously, this was n, this was k, so this was n factorial over n minus k factorial. And that gave me a solution of 720. So if I look at the different options of candidates, if Abby, Ben, and Carter are chosen, so Abby, Ben, Carter, Ben, Ben, Abby, Carter, you get the idea. Looks like there are 6 of them that are similar, meaning that they include the same candidates. So when order matters, when we're dealing with permutations, those are all separate choices. But if instead of choosing a president, vice president, secretary, I'm now just choosing 3 people to be on a committee, in that case order wouldn't matter. And therefore, everybody here in my little table is exactly the same committee group because it's a committee group that includes Abby, Ben, and Carter. So essentially what happens is I have to divide my permutation group that I had before, which was here, including the 10 factorial over 7 factorial, and I have to divide it by 6. So where did 6 come from? Well, notice that k factorial, k was 3, is 3 factorial. 3 times 2 times 1 is 6. That's where that little 6 came from. So obviously, we need a mathematical way to express it, and of course we have one. If we are dealing with a combination instead of a permutation, a combination where order makes no difference, then we're going to find the permutation and we're going to divide it by k factorial. So if I take that to the next step and say, well, I know that this is actually n factorial over n minus k factorial, and then I have to divide that by k factorial, notice all I'm doing is sticking another k factorial on the bottom. So this is my formula for a combination of n items. Choose k. So using our example, again, 10 choose 3, this time for a committee rather than specific positions on the committee. It would be 10 factorial divided by 3 factorial, and then n minus k, which is 7 factorial, and that gives me the 120 that I already knew was the solution. Let's take a look at how to do this on our calculator. It's essentially the same process you're going to go through as before. Math, arrow to probability. Previously we chose NPR for permutation. Now we're going to choose NCR for combination. And again, we're going to plug in 10, 3. I should note, in case your calculator is a touch older than mine, that for some of these you will actually get something with a C, and then you'll have to enter in the parentheses 10, 3, just as we write it on our papers. So it kind of depends on the age or the style of your calculator. So when we dealt with permutations, we said, okay, we can write it like this, but then we put it in our calculator, it looked like this. And obviously we just saw on the last page that the same holds true for combinations, but what we haven't talked about before is this guy right here. And from this point forward, this is how you're going to see these numbers. Notice this is not a fraction. There's no fraction line in between. And this is n choose k. So when we have n choose k, it automatically means that it's a combination, not a permutation, in which case the order obviously does not matter. And then below I just have a couple of things that's important to understand, that if you have n choose 0, so you have n objects and you're not choosing any, there's one way for that to happen, and that's not to choose any of them. or n choose n if I have, say, 10 objects and I'm choosing all 10. Because order doesn't matter, there's just one option for that. Another one that will come into play actually quite often is this guy. This will come into play when we start doing proofs and things. You might have to replace n choose 1 with n choose n minus 1. And again, it's the same idea. It's saying if I'm choosing one thing, then there's n different ways to do it. Or if I'm choosing essentially all but one thing, then there's n ways to do that as well, because you would be leaving one out each time. So let's take a look at Powerball. Who plays Powerball? A lot of people. Is it worthwhile? Well, let's take a look at how many combinations there are. There are 5 balls chosen from a bin of 69 white balls and 1 red ball chosen from a bin of 26 red balls. Find the number of combinations. So let's start with the number of white balls. There are 69 white balls. How many of those are we choosing? We're going to choose 5 of those. So 69 choose 5. Now notice I haven't found that as a raw value yet. That's just 69 choose 5. Same thing for red balls. How many red balls are there? 26. How many are we choosing? Just 1. 26 choose 1. Because I'm choosing 5 white balls and 1 red ball, that means we're using the rule of product. We're multiplying. And so I would have 69 choose 5 times 26 choose 1. Now, if I use the product rule, this is how many different options there are. How many of those options are winners? If we wanted to now talk probability, just 1. So that would be 1 divided by 292,201,338. So are you probably going to win the big jackpot? Probably not. So instead of me taking you through several easy examples, I want to jump right into the hard ones, the ones that make you think a little bit. So obviously I already have this answer out here for you. I didn't cover anything up, but I'd like you to just kind of stick with me so that I can walk you through this. This question says, how many arrangements of the letters in Mississippi have no consecutive S's? So the idea here is that I have 1, 2, 3, 4 S's. And I don't want any of those S's to be next to one another. So I'm just going to put 4 S's so that I remember how many I have. And essentially each of those 4 S's I want to have some letter in between because I don't want to have any consecutive S's. So if you'll notice, I've taken the rest of the letters of Mississippi and I've said there's 1, 2, 3, 4, 5, 6, 7, 8 different positions where I can put the S's, and any of those positions would be okay. So in terms of placement of the 4 S's, I have 8 choose 4. 8 choose 4, meaning I have 8 positions in which to put an S, and I'm going to use 4 of those positions. So that's all well and good, and that would be my final answer if the M and the I and the I and the I and the P and the P and the I had to stay exactly where they are. But they don't, because remember, we're arranging them. So instead, let's take a look at how I might mix this up a little bit. The placement of the other 7 letters is a permutation. So notice this was a combination because all of those S's are the same and it doesn't matter which one I put where. This guy is a permutation because what I'm saying is I'm going to permutate the 1, 2, 3, 4, 5, 6, 7 letters that I have left over. The order of those is going to make a difference because it's going to be a different arrangement. So again, that's 7 factorial over 4 factorial, 2 factorial. Now where did that come from? Well, 7 factorial because there are 7 letters and I'm using all 7 of them, but because I have some repetition, I've got 1, 2, 3, 4 i's, that's the 4 factorial, and I've got 1, 2 p's, that's the 2 factorial. So our final solution by rule of product is this guy right here. And notice I didn't take the time to multiply it out, and that's okay. I'm more interested in, do you know how to find the solution? It's fairly customary when you're learning about the binomial theorem to talk about Pascal's triangle. So before I talk about the triangle below, I want to talk to you about subsets. So let's say I have a set of values 0, 1, and 2, and I want to list all of the subsets. It's best to go about it in an organized manner. So of course I could have the empty set, which is not choosing any of them. I could have the set that includes 0, the set that includes 1, the set that includes 2, and those would be all of my sets with just one element. I could have subsets with 2 elements, so 0, 1, 0, 2, or 1, 2. Or I could have a set with 3 elements, which would of course be the set that I started with, 0, 1, and 2. So I have 1, 2, 3, 4, 5, 6, 7, 8 total subsets. So let's say I didn't have just 3 tiny little elements in a set and I had 100. Well, how would I then determine what I'm dealing with? Well, this is where Pascal's triangle comes into play. So let's say I have a 0 set, which is an empty set. That has one subset, which is of course the empty set. Let's say I have a 1 set, meaning there's only one element. Then it has 2 subsets, the empty set and the only element in the set. Now, before I continue, let's look down here. This would be for my empty set. 0, choose 0. Okay? This would be for my 1 set. I have one element, and I can either choose 0 or I can choose 1, either one. And that's what I've listed so far. So now let's take a look at my 2 sets, which is that I have 4 subsets. I have the empty set, which means I choose 0, I can choose 1, or I can choose 2. And then I have my 3 sets. Well, we already went through this one above, up here, because that was a 3 set. I can choose 0, I can choose 1, I can choose 2, or I can choose 3. Now, this Pascal's triangle translates to these values. 0 choose 0 is 1, 1 choose 0 is 1, 1 choose 1, etc. Now, what do these pertain to? Well, if you look at this row, which we looked at in more detail, I had 1 set that included nothing. I had 3 sets that included 1. I had 3 sets that included 2, 3 choose 2. And I had 1 set that included 3, 3 choose 3. Again, why is this helpful? Well, we can also continue this triangle by adding the 2 digits above it, one to the right and one to the left. So if you'll notice, these 2 add up to 3, these 2 add up to 3, this plus nothing adds to 1, we get the idea. Now, mathematically, what does it mean when I say that I can take 1 to the left and 1 to the right and add them together to get 2, or to take these 2 to add them together to get 3, or these 2 to get 3? Well, essentially what it means is that n choose k, say this guy, can be found by n minus 1 choose k. So this n would be 3. This would be n equals 2. So this is saying take 1 before it, which means the row before it, and then do k minus 1, and then do k. Now, again, that might seem silly, but this is going to come into play all over the place. So this is one of those formulas that you write down on whichever special page you have to write down your special formulas on that you never want to forget. So in this course, we're going to do a lot of proof, and I'll often ask you to do one of 2 different kinds of proof. prove combinatorially is something that you have never done before. So we're going to take our time on this one. To prove this combinatorially, essentially what we're going to do is we're going to find a word problem that represents the situation, then show the expression is true. So this is not like an algebraic proof, and I'll show you that one in a little bit. Essentially, I want to think about how I could model n choose k and make it make sense for this formula. So explain it in a way that makes sense in a story problem, essentially. So for instance, here's one example. Let's say there are 5 applicants vying for 3 similar positions. So notice, instead of choosing n and k, I've chosen to use 5 and 3. So 5 choose 3. Now, I know that I can mathematically find 5 choose 3, but that's not what I'm concerned about. My concern is, how do I make this part of the expression make sense in terms of that I have 5 applicants vying for 3 similar open positions? So I can say person 1 is either chosen for the job, or, rule of sum, because it's or not chosen. So if person 1 is picked, there are 2 open positions left for 4 applicants, modeled by 4 choose 2. If person 1 is not picked, then there are 3 positions left for 4 applicants, modeled by 4 choose 3. So let's take a look. Is it true then, what I just said in the story problem, that says 5 choose 3 is the same as 1 minus that, and 1 minus k, I'm sorry, k minus 1, n minus 1, k minus 1, which would be the 4 choose 2, and then n minus 1 k, 4 choose 3. So in my story problem, that seems to make sense. If person 1 is chosen, then there's only 2 positions left for the 4 people left over. If person 1 is not chosen, there's 3 positions left for the 4 people left over. So if I do 5 choose 3, again, you can use your calculator for that. I get 10. 4 choose 2 is 6. 4 choose 3 is 4. Notice 10 equals 10, so I've proven this combinatorially. Let's take a look at that exact same expression and now prove it algebraically. So now, instead of making up a fun little story problem about people vying for a job, I'm saying, let's look at the math here. So this is going to be mathier than our combinatorial proof. So we're saying we have a typical n set being that there are n elements in the set, and we consider 2 types of subsets. Those that contain a sub n, which is whatever our last guy is, and I could have said a sub 1 too, it doesn't matter, and those that do not. So if a k subset of A does not contain a sub n, then it is a k subset of a sub 1, a sub 2, etc., all the way to a sub n minus 1. And there are n minus 1 choose k of those, because again it's a k subset. If it does contain a sub n, then it consists of a sub n and not k elements, but k minus 1 element, because I've already said this guy. So instead of k, it's what k minus 1. So that's this guy. Since there are n minus 1 choose k minus 1 of these, and there are n minus 1 choose k of the other subsets, my total number of subsets looks like this. So essentially what I've done is I've said, if I have n choose k, which is where I started, and I break it into subsets, those are the 2 subsets that I get, which proves this algebraically. Here is another combinatorial expression that I would like you to prove is true, that n choose k is the same as n choose n minus k. So prove this not algebraically, but prove this combinatorially. When you are ready, press play to see how you did. So keep in mind that you could have described this differently than I do. I just went straight for the 5 applicants vying for 3 similar positions again. And what I can say is 5 choose 3 is me choosing 3 of the applicants to fill the positions, and n choose n minus k would be 5 choose 2, which is essentially me saying I'm choosing 2 applicants that will not fill the position. And then I'm also showing here that if I took 5 choose 3, I would get 5 factorial over 3 factorial 2 factorial. If I choose 5 choose 2, notice I get the same thing. It's a little bit different order, but we know that that doesn't matter with multiplication. So before we continue, let's just review sigma notation very quickly. When finding the sum of a series, like a sub m plus a sub m plus 1, etc., all the way to however many values we have, we can instead use sigma notation, which is the summation notation that says take the summation of all values starting at m through m plus n, where I is being replaced by m through m plus n, essentially. The I is called the index, and we can use different letters for I, often J or K, but most of the time you will see it as an I. And again, it's simply a method to denote the ith item in a series. So for instance, if I said I equals 5 through 9, so find the summation from 5 to 9 of a sub I, that would mean a sub 5 plus a sub 6 plus a sub 7, a8, a9. And again, what are those numbers? I have no idea because I didn't give you the series. So if I gave you the series, and let's say it was just my counting numbers, then you could say a sub 5, so this is a sub 1, this is a2, the second item, this is a3, a4, a5. But they don't always match up like that. So it could be that these numbers were 2, 4, 6, 8, 10, 12, you get the idea. So this is just saying the 5th item in the series, the 6th, the 7th, the 8th, the 9th. Let's remind ourselves of a few properties before we move forward with summation notation and why we're talking about it right now. So a couple of properties. First of all, if you've got, this one's kind of silly, I wouldn't even consider this one a property, but essentially we're saying, look, if you're taking some constant times I being the index that you were plugging in, that it's not going to change anything if I include the 0, because 5 times 0 is 0, and so it's not going to change my sum at all. So that one's kind of silly, and honestly you don't come into contact with it that much. The second one you use all of the time, and this is basically says if you've got a number like 5, it's okay to pop it to the outside, because essentially what would happen if I took the summation 5 times the summation of this, it would be 5 times 1 plus 2 plus 3 plus 4, and it would give me the exact same thing that I had here. This one you also use a lot if you don't have an I in what you're finding the sum of. Essentially, each time you use the index, this is the first, second, third, fourth, all you're doing is just writing x again. So my solution, if I wanted to simplify, is 4x. And the last one, this one's for those tricky examples, because sometimes we have to be a little bit tricky with our math. If I'm finding the summation of I squared, I can alter those limits, the lower end and upper end of my index, to adjust to a certain situation. So here I'm taking, notice I've added 1 here and added 1 here, because here I subtracted 1 from I. So still this would be 2 minus 1 squared, which would be 1 squared. And then 3 minus 1 squared, which would be 2 squared. Same thing if I go in the other direction. Here I subtracted 1 and subtracted 1 because here I added 1, and it would be the same thing. So we've looked at quite a bit so far, and it hasn't necessarily all melded together yet. And this hopefully will meld everything that we've talked about in this section 1.3 together. So we've talked about Pascal's triangle. We've talked about how to write a binomial value like 4 choose 2, n choose k, etc. And we've talked about summation notation, but why? Why did we talk about summation notation? It doesn't seem to fit. Well, let's put it all together. Let's say I have a binomial. Binomial being that I have two values being added or subtracted and raised to some integer power. For example, x plus y to the third tells me to take x plus y times x plus y times x plus y. And I know that if I were actually going to multiply this out, I would take two of them and FOIL them to get x squared plus 2xy plus y squared. And I would still take it by that last x plus y. And when I multiplied this out, I would end up here. 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Now, why do I care? Why is that important to me? Well, let's take a look at 1 and 3 and 3 and 1. Those digits, if you'll remember, are from the third row of Pascal's triangle. So remember I had 1, then I had 1 and 1, and then I had 1, 2, 1, and then I had 1, 3, 3, 1. Those numbers are the same as what I just used in my answer. So for that reason, the number n choose k, because if you'll remember, this was 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So n choose k are often referred to as binomial coefficients. So the binomial theorem says that if you have a binomial raised to an integer power, that it's going to follow this format, where I'm taking n choose 0, a to the n, and notice that held true here. N choose 1, I'm going to decrease the a exponent by 1. I'm going to increase the b exponent by 2, because essentially this was b choose 0. I'm sorry, b to the 0. And then that pattern is going to continue. This goes down 1, this goes up 1, etc., 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 all the way until the end, where I'm going to have a to the 0, b to the n. Now, why did we review summation notation? Because that can be simplified into this. So the binomial theorem is often written as this equals this, which is to say the summation from 0 to n of n choose I. So I is the value that's going to change 0, 1, 2, 3, etc. of a to the n minus I, b to the I. So we'll see a lot more applications of this further down the road, but one application we'll use immediately will be a question like this, where it says use the binomial theorem to determine the value of the coefficient, coefficient of course being what's the number that's going to go in front of x to the third, y to the 8th. Now, what I would not want to do is to take, because there's obviously 11 total, what I would not want to do is actually multiply x plus y out to the 11th, because that would be a lot of work for something that I don't need to show all of that work for. So instead what I can do is I can say, well, I have 11 and I'm going to choose 3. Or I have 11 and I'm going to choose 8. Now, how can I do that? Well, because of that theorem we talked about before that says n choose k is the same as n choose n minus k. And I know 3 and 8 are my two numbers because those are the two numbers here, and of course these add up to 11. So then I can just get my calculator out to compute what that is, and that's 165. So what does that tell me? That tells me if I were to take the time to multiply x plus y, blah, 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 x plus y, 11 total. If I took the time to FOIL those out, combine like terms, FOIL it out again, combine like terms, etc., the term that included x cubed y to the 8th would have a positive 165 in front of it. And then I could continue to find those values. So here are a few corollaries, and I would encourage you to look at them both in detail. particularly the first one, you might see it again. But how does the binomial theorem that we just talked about lead us to this? So I'm not going to go through that with you. I believe it's in your textbook. If not, obviously, you may Google. But I want you to actually struggle with it a little bit before you just Google to find the answer. We're going to finish out with the multinomial theorem, and that essentially is for when we don't have a binomial, but we have several values that are being added or subtracted, taken to an integer power. Now, this guy looks like a hot mess, and so I don't even want to really explain it to you until I can show you an example. So let's just put this on hold for just a moment and go look at the example together. So let's take a look at this example. If I didn't give you the multinomial theorem, we would just have to plug and chug through this and take a plus b plus c times a plus b plus c, and we know it's pretty straightforward. It's just that it's going to take a while, and that's just the a's, and then I would have to do the b's, then I would have to do the c's, then I would have to combine like terms. Now, for something that was squared like this one actually might be shorter, but let's take a look at what the multinomial theorem will help us to do. So this would be our first line of work, and don't freak out yet, because here's what all of this means. I know that I'm going to have some value a squared, and then some value b squared, and then some value c squared. That's this first row. And where do I get the numbers? Well, this is the multinomial theorem that says n is 2, and I'm choosing 2, choose 2 a's, 2, choose 2 b's, 2, choose 2 c's, and notice that corresponds to how many a's, b's, and c's I have. So essentially that would give me these fill-in-the-blank options. Then I know that in addition to those, I'm going to have something AB, I'm going to have something AC, and I'm going to have something BC. And how do I get that? Again, that's these guys. So 1A, 1B, 1A, 1C, 1B, 1C. What do those multinomial coefficients turn into? Well, essentially what we're saying is take 2 factorial over 2 factorial, 0 factorial, 0 factorial. Same thing here. 2 factorial, 0 factorial, 2 factorial. Keep in mind that 0 factorial is 1. And then that's for the third. And then for the next line, 2 choose 1, choose 1. 2 choose 1, choose 0, choose 1. 2 choose 0, choose 1, choose 1. And then use your calculator. A squared, because 2 factorial over 2 factorial is 1. So a squared plus b squared plus c squared. And then 2ab, 2ac, 2bc. And if you don't believe me, please feel free to multiply this out and to determine the final solution. But you should end up with what we ended up with here.